I've been building battery systems for over 10 years and today I'm going to tell you all I know about batteries. Almost everyone is familiar with standard batteries like the button cell, the AA cell or standard 9-volt cells. You'll find these in any household items to power the electronics. They're very safe, but they have a low energy density, so you need to replace them quite often depending on the application. Next up, lead-acid batteries. They're 12 volts and they're found commonly in cars and in trucks. They're very powerful, they can deliver a lot of current and they allow a start engine to be started. If you put two lead-acid batteries in series, you get a 24 volt battery system. This one is small, so it has less capacity than this one. Lead-acid batteries also have a downside. They're very heavy and their energy density is very low. Lead-acid will burn your skin and it's very bad for the environment. Now on to my personal favorite, the lithium-ion 18650 battery cell. This is the workhorse in most small battery applications. They are very efficient, they have a really high energy density and they're very light. Now what does 18650 actually mean? It's the dimensions of the battery, 18 millimeters diameter and 65 millimeters long. This is the industry standard for a long time and you can still find them in a lot of applications. The nice thing about these 18650 batteries is they're really flexible. You can easily configure them to create any voltage or current that you desire. For example, if you put two in series, they're 3.7 volt each, there's 6.5 volts nominal voltage. But you can also take 4 in series and you can roughly approximate a 12 volt battery like this one. You can also put them in parallel. The advantage of putting batteries in parallel is that you increase the capacity of the battery. If you put them in series, you increase the voltage. Now why would you do that? Increasing the voltage allows you to deliver the same power output but with lower current. And lower current means less losses. Alright, on to a real life example now. This is a battery pack from a battery powered drill. It contains lithium-ion batteries, the 18650. This battery pack contains 8 cells and they're stacked into it like this, 2 rows of 4. You can also go one size bigger. For example, this e-bike battery. They are also powered by 18650 lithium-ion battery cells. The configuration of this one is 10 in series and 5 in parallel. So if you look closely at this housing, they've made a lot of effort to neatly pack in these batteries so it fits. It's really impressive. This is another really nice example of batteries. This one is from a data center and it's used in a UPS, meaning uninterruptible power supply. As you can see, here on the inside is a little compartment and here are the 18650 cells. They're used for when the grid goes down, the computers still stay on as a backup power supply. Let's go one step bigger. This here is a Tesla Model S battery module. In one Tesla Model S are 16 of these modules. Inside this module is a lithium-ion 18650 cell. This module contains 444 of these cells and there are 6 groups in series of 74 cells. In a Tesla car, 16 of these modules are put in series to create a 400 volt system and this drives the powertrain of your car. So far we've looked at the 18650 cell, but there's also a different form factor of this cell and that's the Prismatic module. The benefit of this module is that it's way larger and it's rectangular, so it's much easier to put them together. And for space it's much more efficient because with these cells you have a circle and with this you have a rectangle, meaning you can put more energy in the same footprint as with a circular battery. Okay, so we've discussed the Prismatic batteries modules. You can put them also together into a pack, like this one. So this module, you can stack them together and make a 4S 2P battery pack if you want to. You can see here the battery modules are stacked together, like this. And they're connected here by 4, 4 and 4. This is also one of the building blocks for a battery system. It's quite simple, but it works really well. The nice thing about these prismatic batteries is that they come in all sizes and shapes. For the EV industry, cars, it's really important to be really compact. So this prismatic battery can also be made a bit smaller and wider. What you get then is this 16S 2P pack. This battery module is from a Mercedes EQS series. If we open them up, you will find 32 prismatic cells inside this module. They're configured 2P16S, meaning there's 2 modules in parallel and 16 in series. The way they've done it here is that this is a battery and this is a battery, and they go like this. We make a string in series all the way to here, so you have the plus and the minus on the outside. And this is the battery. Now this module is not the only thing you can make with prismatic batteries, because they come in all sizes and shapes. You can also make them even smaller and wider, so you get a different variety of modules, like this one in the BMW, or this one from the Stellantis group, which is mainly the French auto manufacturers. What we haven't talked about is different chemistries, and there's a new kid in town. Since a few years, LFP chemistry is slowly taking over the market. What's the difference? Well, the main difference between LFP and lithium ion is LFP is lithium iron phosphate, and the chemistry is slightly different, so it keeps a little bit less energy, or the energy density is a bit lower, but it's much safer. For example, this is an LFP module, and this module you can even hit a nail straight through it and it shouldn't catch fire. If you do that with a lithium ion battery, it will definitely catch fire. The downside is it is a bit heavier and therefore you get less energy density. So this is why I expect that in the next few years the industry is gonna completely change from lithium ion, these modules, to lithium iron phosphate, this one here. Let's talk safety, the battery management system, or the BMS. In this system you can find it right on top, and its sole responsibility is safety of the battery module. We've talked about before that you can put multiple batteries in series, but in general you only measure between the plus and the minus at the end of the battery pack, but you don't know what the voltage is in between of the individual cells. Overcharge a lithium ion battery, it can easily catch fire. The battery management system measures the voltage of each battery in the pack, and it makes sure that the voltage of the batteries is between the limits that is set for the specific battery. For lithium ion you go to 4.2 volts on the top end and about 3 volts on the bottom. For lithium iron phosphate you can go to 3.6 volts on the top and 2.8 volts on the bottom. What happens if you exceed those voltage ranges? Quite simple, with lithium ion it will catch fire. It is very dangerous to overcharge them, and therefore every single system always needs a reliable BMS. Lithium iron phosphate, however, is a bit more robust. It won't catch fire, but you will definitely destroy the batteries if you overcharge them or drain them too far down. Another very important feature of the BMS is to measure the temperature. If the batteries get too hot, they might experience thermal runaway and catch fire. Also a big risk. Just to recap, the battery management system is on top. It measures the voltage of each individual cell and it also measures the temperature, so you can keep your battery pack in your car safe. Every day in the news you will hear a new development on the battery technology. Whether that be sodium ion batteries, solid state batteries, there's always something new. So what do I think that's going to happen in the next 5 to 10 years? I'm not quite sure, to be honest. I think lithium iron phosphate batteries will most definitely gain the biggest market share. And for the new technologies, as long as it is not mass produced in electric vehicles, cost effective, at scale, they don't exist. Because it's really easy to make something in a lab, really impressive, but it's even harder to make it at scale and cost effective. These were the basics of battery systems most commonly found today. Let me know what you're curious about and what you would like to see next.